All right. Introduction to circuits. So we're going to see circuit diagrams, and batteries are represented like this, resistors like this, and wires like this. These are the things that we'll mostly see. A switch is like this. So you see how if you rotated this down, you would then have a wire for the current to pass through. And sometimes we talk about things being grounded, meaning connected to ground or some large source of charge, like a car or something. So you may have seen the negative terminal in off a car battery that's just attached to the car body. It is grounded that way. And then a voltmeter or ammeter, measuring current, measuring voltage or potential. So first, let's talk about a little example where mostly we idealize batteries as having no internal resistance, but the reality is that they do. So this E here is called electromotive force, or EMF. Electromotive force is what voltage was first called way back, and physics people still use that. So the voltage here, the voltage here is 12 volts, and it looks like there's a little resistor drawn right next to the battery. We're talking about an internal resistance of the battery, because the chemical processes that happen in order for the charge to flow don't happen instantaneously. So what a battery does is it pushes electrons against an electric field. The analogy would be the hand pushing the ball. So gravitational field is like this, right? And the hand pushes the weight or mass or ball against the gravitational field, and then when we let it go, it just sort of falls instantaneously. Same thing happens with the battery. Battery pushes the electrons towards the negative terminal so that when the circuit is complete, they simply release and flow through, just like the ball flows through the air towards the ground. Okay, so here's our circuit. We have a battery and then a resistor, 65 ohms. And the question asks a couple things. So wait, electromotive force we talked about, and then internal resistance. Okay, so you could describe what those things are right there. So what is the current in the circuit? What is the current in the circuit? What is the terminal voltage of the battery? So it's not like terminal velocity or a terminal illness. Terminal voltage refers to the terminals of the battery. So these guys, if we're talking about a car battery, it would be taller than that. And these are the terminals. So basically, when you hook something up to the battery, what's the voltage? That's all that means. And then power dissipated in the resistor. So we have that one big 65 ohm resistor. What power is dissipated in it? So, current in the circuit. Here's a redrawing of our circuit. And the total resistance is actually 65.5 ohms because of that little internal resistance of the battery. So using Ohm's law, V equals IR, voltage, current, resistance, and we divide and we end up with something like this, 0.183 amps. So this is the current in the circuit. Current in circuit, and sometimes it will be described as total current in the circuit when we get more ambitious. Okay, so terminal voltage of the battery. So we would expect the battery to be 12 volts, but some of that is used up in pushing electrons across that resistance. So that's what we mean by terminal voltage. So the voltage across the battery terminals is going to be 12 volts minus the voltage drop across the internal resistance. By voltage drop, we mean voltage used up. So we're just using V equals IR right here for the current, and then the resistance of the internal resistance of the battery. So 12 minus, this is voltage drop across the internal resistance, gives us 11.9. So notice how that's very similar to 12. Okay, terminal voltage. Lastly, power dissipated in the 65 ohm resistor. So I think I've calculated this two ways, where we know that the current through the 65 ohm resistor is this many amps, and we know the voltage across it is 11.9. That's what the battery is actually putting out. So we can multiply and we get 2.18 watts. I use one of those variations of the power equals current times voltage. So the current squared times resistance. Here's current squared, here's resistance of that resistor, and so we get this many watts being dissipated in the resistor. Notice how we get the same answer. They both work. That's kind of cool when you have a choice or many ways to solve. Sometimes students don't like that because it means they have to choose, but okay. So this is the steak and potatoes of this unit, okay? Resistors in series and resistors in parallel. Let's look at the difference first. So resistors in series, try not to pay attention to all those answers there. We have a battery, and notice how the current, okay, conventional current goes from the positive terminal. Notice how the current has to pass through both before it gets back to the battery. It has to overcome a 4 ohm resistor and a 2 ohm resistor before getting back to the battery. Series. Parallel, okay, don't think that this is just because of the orientation of these resistors, okay. Parallel refers to a situation where the current can pass through this 2 ohm resistor and return to the battery, or the current can pass through this 4 ohm resistor and return to the battery. So some of the current's going to go this way and some of the current's going to go this way. And because this path involves least resistance, we expect more current to flow that way. Okay, so that's the difference between parallel and series, and we're going to calculate a bunch of things. So here's what we're going to calculate for our series circuit here. We're going to calculate the equivalent resistance of the circuit, meaning these two resistors together, how much resistance do they put up, the current through the circuit, power dissipated in the circuit, and then basically the same thing for each of the resistors. So here we go. So here's a formula, and sometimes it's written like this: R1 plus R2 plus R3 plus dot 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 dot. However many resistors you have in series, you simply add up the resistance of them to get the total resistance of the circuit. So because the current has to pass through both, it's a total of 6 ohms of resistance. So our equivalent resistance of the circuit is 6 ohms, and we got that from 2 plus 4. Piece of cake. The current through the circuit, so we'll be using V equals IR, I like this orange color. The voltage is 12, and the current is I, and the resistance of the circuit is 6. So dividing gives us a current through the circuit of 2 amps. That was in amps right there. Power dissipated in the circuit, that would be heat. So let's see, P equals IV, so we know that we have a current of 2 amps, and we know that we have a voltage of 12, giving us a total of 24 watts of power being dissipated in the circuit. So used up, and that would be, they would be heating stuff up because the power is dissipated as heat. Okay, voltage drop across each resistor. So this concept is, this is something to think about. Voltage drop. So think of the voltage as like a force. Okay, 12 volts of force to push the electrons through here and to push them through here. So by the time they get through this, okay, think of it as a mountain range. By the time they get through there, it's easy sailing, smooth sailing, and the electrons just cruise back to the battery, and or the current cruises back to the battery, resistance free through the wires. So part of the 12 volts is used up here, part of the 12 volts is used up here, and by the time it gets through here, all of the 12 volts has been used up. So how much is used up here and how much is used up here? So this is the writing here. We already know that the current through the circuit is 2 amps. We figured that out. So just looking at this individual resistor, we know that the current through it is 2 amps, and its resistance is 2 ohms, so the voltage drop across it will be 4 volts. Okay, so let's see if that makes sense based on the other resistor. This other resistor, we know the current through it is 2 amps, and the resistance across it is 4 ohms, yielding a voltage drop of 8 volts. And you're probably going, aha, because 4 plus 8 is 12. So the battery provides 12 volts of voltage, and 8 is used up on the big resistor, and 4 is used up on the small resistor, and all 12 is used up. So if you calculate the voltage drop and you go, okay, it adds up to the voltage of the resistor, you can pat yourself in the back. Alright, what else are we doing here? So the voltage drop across each resistor, we just have labeled up there, it was 4 volts and 8 volts. Notice how it adds to 12. Yeah. Power dissipated in each resistor. How hot would they be getting, I wonder? So let's see. PIV, P equals IV. Power is current times voltage, so the current through here is 2 amps, and notice how we just calculated the voltage drop across it. And you could also probably do the I squared R, not probably, you could do I squared R, it would work. And so we got 8 watts being dissipated or used up by that resistor. If we go through a similar color-coded calculation, current times voltage, so 2 amps times 8 volts drop across this one, we get 16 watts. Alright, so let's see, 8 watts plus 16 watts is 24 watts. Did we calculate the power through, or power dissipated by the circuit? Aha, we did. Look at that. Okay, so notice how the power dissipated in one resistor and then the other adds to the total power dissipated in the circuit. Good work, us. Alright, so what else do we have? So we calculated these, they're listed here, and the current through each resistor, well, that we already found. So the current through the circuit was 2 amps, and because that has to pass through here and here, the current through each resistor was simply 2 amps. Okay, so series circuit, these are the easier ones. So we will draw a smiley face next to them. Okay, let's take a look at parallel circuits. So resistors in parallel, equivalent resistance first. So some people like this hallway analogy where we have a gym full of students, right, and they have to leave through this hallway and either pass through this door or pass through this door in order to get out to freedom, right? And so a larger resistance, that would be a smaller doorway, and a small resistance, meaning a larger doorway. So some students would pass through here, some students would pass through here. The way we actually calculate the equivalent resistance is a little more involved. So it's this reciprocal situation where we do however many resistors we have in parallel. We say 1 over the equivalent resistance, so you should write that this is equivalent resistance, 1 over R1 plus R2 plus R3, etc. So here's how we set this up. 1 over the equivalent resistance of our circuit is 1 over 2 ohms plus 1 over 4 ohms. Oh good, we get to practice our fractions. Love it. So common denominator is 4. 2/4 plus 1/4 is 3/4. And 1 over R equals this, so we could cross multiply or just flip them, and we'd get that the equivalent resistance of the circuit is 4/3 ohms. So let's write that down. Equivalent resistance of the circuit, 4/3 ohms. Okay, so take a look. Up here we had a 2 and a 4 ohm resistor, and together they made 6 ohms of resistance. Down here we have a 2 ohm and a 4 ohm resistor, and together they make 4/3 ohms, which is much less. I know this is all over the place. This is much less than this. And this is because there's now a choice of paths, and the current only passes through one, not through both. So always, not just in general, but always, parallel circuits, the resistance is going to be much less than if you connected them in series. Also notice how the 4/3 is less than 2 and less than 4. It will always be less than either. So the equivalent resistance in a parallel circuit will always be less than any of the resistors. That might be a good thing to write down too. Current through the circuit, we are plugging away. So let's see. V equals IR. Our voltage across the circuit is 12 volts. Current is what we're looking for. Our resistance is 4/3 ohms. More fraction practice. Looks like 36 over 4 is a 9 amps. 9 amps. Notice how that is a lot more than the current in the previous example up top, right? Less resistance, more current. That's how it works. Power dissipated in the circuit. Need a little more space here. Try to color code. Alright, power dissipated in the circuit. So what do we know? P equals IV, and our current through the circuit is 9 amps. Voltage across the circuit is 12 volts. A whopping, 108 watts. That's a lot. Current through each resistor. So I think that I pre-calculated these up here. So if we're looking at the 2, alright, so what would be the voltage? This is where things get different. So we have this situation, right? Notice how this resistor has wire directly connected from the battery. So it's experiencing 12 volts across here. Yet this resistor over here is also directly connected via wire straight to the terminals of the battery. So it also is going to experience a voltage of 12 volts. So that's different from what we saw above. For our 2 ohm resistor, the voltage is 12, the resistance is 2, and so we have 6 amps of current flowing through here. Actually, I'm going to put that in blue because it's current. Okay, and when we go to calculate the power, we know it's current times voltage. Again, the voltage is 12. Notice how it's a 72 watts across this guy. Not that the resistor would be male or female, but you know. Okay, for the 4 ohm resistor, V equals IR, so we got 12, a current, and a resistance of 4 ohms. We solve, we get 3 amps. Notice, please, how this has half the resistance, and so it gets twice the current. Aha! Yes, things work like that. And so power is current times voltage, and we get 36 watts. So please note that together, the power dissipated was the power dissipated in the circuit that we calculated previously, and together the currents, the 6 amps plus the 3 amps, yield a current of 9 amps, which is the current through the circuit. Whoa, dude. That's so cool how it works out. So I think we calculated everything we were asked. We got the voltage drop across each resistor, 12 volts and 12 volts. You could write that in here. Power dissipated, 72 watts, 36 watts. Okay, so don't hang up yet. This, useful piece of information. So I would find some space on your notes. It was pretty busy notes, but you'll find some space. And write down this graphic organizer where we have series and we have parallel resistors. What do we know about the voltage drop, current through each resistor? Because what we just dealt with was for the resistors in parallel, the voltage drop across each was same as the battery. Whereas for resistors in series, they added up to the voltage of the battery. And so it's vice versa when we talk about current. Resistors in series, the current had to flow through each, and so it was the same. Yet for resistors in parallel, there was a choice, so the current through each, we add them up and we got the current through the total circuit. But then for the power dissipated, we add them up for both situations to get the total power dissipated by the circuit. Look at this useful stuff. Oh my gosh.